Hello, it's Keith here, and this is lesson 5 of the MaxTile series of my Z80 assembly programming tutorials. What is MaxTile? Well, it's the software tile map code you can see on the screen here. It works as a software tile map on some systems. On systems with sufficient hardware tile map capabilities, it does use the hardware tile map functionalities, and is multi-platform, so you can draw the same tile maps on different systems in the same kind of ways. Now, what we're looking at today is the cache driver code. We looked last time at the direct driver. This draws directly to VRAM, and that's designed for double buffers, but you can use it without a double buffer if you don't mind flickering. However, the cached version is designed to reduce flicker where there is only a single buffer, so there's no screen buffers being used here. You can see there is some flicker. It just depends on the amount being drawn and the timing of the raster beam. Now, actually the caching routine uses 3 caches. 3 different strips of the screen have 3 separate caches, and the code automatically pipes the data to draw into the separate ones. The idea being that you can synchronize the drawing of these to the raster beam, so when the beam is here, you can draw the top third. When the beam's here, you can draw the middle third, and so on. This does actually slow down drawing a bit though, so it's actually disabled here, but the caching does still reduce flicker because it reduces the amount of time in between drawing the background and the foreground, because that's all been pre-calculated. That's the theory. Let's go over to the code and let's take a peek. Let's see what we've got in today's code. So the code for today is basically an alternative version of the draw tile map routine. The code is executed in the same way. However, now rather than drawing straight to the screen, what it does is it analyzes the lines of the tile map, and it remembers the start and end of each line that needs to be drawn and adds those to the cache. If nothing on a line needs drawing, nothing is added to the cache. And as I say, in that way we reduce the amount of time the drawing of the screen takes from start to finish, and that means the amount of flicker is reduced. Of course, the total drawing time is slightly longer because we're having to read over the tile map first to work out what he's drawing, and then read over it a second time if any of it actually did. But as I say, the overall result is more pretty and doesn't need the amount of memory that would be required for a second screen buffer. So that's what we've got today. Now, the cache itself is made up of 2 parts. There's the actual storage for the data itself. There are 3 256-byte caches that are the actual data that defines the areas to draw. However, there is a table of pointers to that data that is used for the control of the actual caching. That's what we're looking at here. Basically, we have the cache table. These have 3 entries for the 3 sections of the screen. The first entry is the last VRAM byte of the high byte of the VRAM destination. So as bytes are being considered for drawing to the screen, when we get to a certain line, we're going to switch to the second cache and then the third cache. And so the memory address that the CPC does this as is C200. So C2 is the top byte there, and then C400 for the second third, and then the final third works for the entire screen. So FF is a precondition that will never occur. That's beyond the end of the screen. So that's why we've got that there. So that's how we're detecting the switches to the different caches. We then have the address of the caches. You can see that address is there twice. Now the second one never changes, so that is the sort of backup version. The first one will be updated as data is being pumped into the cache. We would run this draw tile map routine multiple times, once for the background and once for the simulated sprites. They use miniature tile maps as well. So address current will be changed multiple times, and address back is used to restore that address current. Finally, we have a byte that is used for the raster timing. Now, I'm not actually using this in today's example because it's a little bit complicated, but on the CPC, this was basically the interrupt count for the time that we wanted to draw these caches. So that's just 1 byte there for that timing option if you decide to use it. Now, the actual addresses of cache address 1, cache address 2, and cache address 3, these are defined in the platform-specific code. So you can see here, we've got the addresses here, and we're basically defining these as various areas of memory, just depending on the system. These need about 256 bytes free. You can actually define the size with cache max bytes, but you do need to allocate enough extra space so that if we are under this count before we add an extra line to the tile map, we're not over it by the end. And so I'm basically allocating 16 bytes there. So each cache is 255 bytes, but we're stopping just before that so that there is enough space for the worst case possible line to be added to that cache. Now, if a cache fills, we have to flush it immediately, but generally we want to wait until we do them all at the same time. Now, There are a total of 3 cache entries. We're defining that there. Each entry is a total of 6 bytes. 1 byte plus 1 byte plus 2 bytes there, you can see, so that's 6 bytes. The offset to the current address and the backup address are there, and the screen position is in there as well. And we use those as offsets for IX registers later on. Now, the specifics of these is defined for each system because the VRAM addresses are different on every system. But basically the routines beyond this are pretty much constant for every system. First of all, we have a routine called get cache IY. This takes the IY register as a pointer to the table and returns the next cache within that table in IX. And it also sets the 0 flag, defined whether there's any data in the cache. This is designed for flushing the caches. We would use IY to point to the cache table, and IX would be returned with consecutive caches within that table. Now, if the 0 flag is set, then there's nothing to draw. You see, a sequence of 3 0 bytes within the cache is the end of cache signifier, and if that's at the start, then the cache is completely empty. The first 0 byte would normally be a count of items on that line to draw, so 0 is impossible, and so that is our command marker. The second 2 bytes after a command marker would be the pattern table, the pattern data to be used to draw this tile map. But if that is 00, that is considered to be a special end of marker. This does create a rather odd limitation for the systems like the Sega Master System, which use the hardware patterns. That can't start from the pattern number 0 because that would be mistaken for an end of sequence command. So you would want to start from pattern number 1, even if you could use pattern 0 for that case. This never happens on the Amstrad CPC, for example, because having pattern data at memory address literally 0 would be overwriting the interrupt addresses of that system. So your reset vectors would all be changed, so probably impossible on that system. But as I say, for the hardware pattern systems it is possible, but it is a limitation that you can't do. Now here is our actual drawing routine. When this is executed, the registers have the values shown here. So DE is the source tile map, DE in the shadow registers is the bitmap pattern data, HL is the VRAM destination, and IY is the tile map width. IXH and IXL are the draw width and height in tiles. So what we're going to do here is we're going to use our caches and draw into those caches. So we're getting the address of the cache table and updating the current position within the cache table for the current cache at cache table address. This will be updated as we process the cache and move down as we go over the VRAM destinations. Okay, so what we're going to do here is we are going to get the next cache within our table. So we're loading the address of the cache table, and we are loading the address of the cache into IX here. We're then setting the H register within the shadow registers to 0. Now this is a flag to notify that we are doing the first entry for this tile map. Now when we want to draw a tile to the screen, if we do, we need to actually update the defined patterns that we're going to use, because different tile maps may use different pattern data. So whenever we draw the first tile of a tile map, we write the pattern data with that command byte, firstly the 00, then the address of the pattern data. Okay, so this is our line loop. So we're going to process a line of our tile map here. Now what we're going to do is we're going to compare the H part of the HL VRAM destination to IYL. We loaded this in up here, and this is the offset that is the end of the current VRAM destinations for our tile map. So as I say, C2 is the end of the first cache for the CPC. That's what we're comparing to now. And if we've gone over the appropriate data for this cache, we will run the over this cache routine. Otherwise, what we're going to do is we're going to process the current line. Now, BC within the shadow registers marks the start and the end of the line that needs to be drawn. So our line might be 32 tiles wide, but maybe there's only a single tile within there that has actually changed, and BC will record that. So what we're going to do is we're going to load in a tile from our tile map, and then we're going to check the bottom bit. Now the bottom bit is the update flag. Now if this is set to 1, this tile needs drawing. If it's set to 0, this tile has not changed and shouldn't be drawn. So in the case that it's 0, we're going to skip over this tile, but otherwise what we're going to do is we're going to see if this is the first tile that needed drawing on this line. Now if it's not, then we're going to skip over, but if it is, then we're going to decide what to do next. Now what we're doing here is we are updating the first tile in B, So that is marking the first tile number that was found. And then what we're going to do is we're going to check the H register within the shadow registers, and we're going to see if this was the first tile that was drawn. Remember, we set it to 0 up here, so this is now a flag. And if it is the first tile to be drawn, we mark it as not the first tile to be drawn for next time. We then write our command byte of 0 and our DE address of our pattern data that we're using to draw this tile map, because we need to do this at least once for the tile map that's being drawn to the screen, otherwise we might be using the wrong pattern data. Now, 16 color systems that use 4 color pattern data have a tint option. This basically sets the top 4 bits of the 16 color entries. This is an extra byte, so on those systems this command byte of 0 has the pattern data followed by a single tile tint byte there, but most systems don't use that. We're then skipping over that data that was just defined as that command byte. But then what we're going to do next is we're going to write the information for this line of the tile. So basically what we write is the start VRAM destination for this line. We then write the starting source tile map data for this line. We're writing these to 1, 2, 3 and 4 offsets within the cache. 0 will be the length of the line, and as I say, a length of 0 is impossible. That's why that is defined as the command byte. A single tile would be a value of 1. Okay, so that's what we've done there. We've written all of that data. Now what we're going to do is we're basically going to continue. Now we found a tile of some kind. It may have been the first or may not. So what we're doing here is we're updating the last tile, and this is going to be used to work out the count of the tiles to draw later. We then move to the next tile in the source tile map, and then we've got some platform specific code to move the VRAM destination across one tile there. We're then going to repeat, so we repeat considering all the remaining tiles on this line. Once we've done an entire line of the source tile map, it's time to decide and see if anything was actually drawn. So we're taking B and C within the shadow registers here, subtracting them. If the result is 0, then there's nothing to draw. We added 1 to these as we were calculating, so the end will always be 1 higher even if only 1 tile was drawn. So if the result is 0, then there's nothing to draw. If the result is 1, then there was 1 tile to draw. We then write the tile count to ix plus 0 here if there is something to draw. Now in that case we've basically written the tile count, the VRAM destination, and also the tile map source, so that's 5 bytes total into the cache, so we add 5 to the ix cache position. We are then going to basically look at the current count of bytes in the cache and see if that's over the limit, and if it is, we're going to run cache full. This basically flushes the cache straight to the screen. Not ideal, will cause some flicker, but if we've got too many bytes in our cache, there's nothing else we can do, so that's what we're doing there. Now after this, we've basically done the entire line of this tile map, and so we're going to do the next line. So what we want to do now is we want to move down the screen in our HL VRAM destination, so we've got platform specific code to do that. And then what we're going to do next is we're going to move down one line of our tile map. So we're adding the width of the tile map in IYH to DE. This is moving us down one line of the tile map within the tile map data. And we're then going to repeat for the entire tile map. Now what we're going to do next is we're going to update the current address within our cache here with the new position, because we've written some data and we need to start from that position next time we write tile data. So that is what we're doing here. We're then going to write the marker for the end of the cache, 3 0 bytes here, because if we don't write any more data, we need to leave the cache in a valid position to draw, because we don't know how many more tile maps are going to be drawn. So that's what we're doing here. Now if we got to the end of a cache, what we're going to do is we're basically going to mark the end position of the current cache, and then we're going to load the address of the next cache, and then we're going to jump all the way back to the top and start processing once again. So we would resume here and continue processing that next cache. So that is if we've gone over the VRAM limit of the current cache. That's what happens there. Now if the caches are full, we write an unexpected end of cache marker here, and then we flush the cache straight to the screen. As I say, not ideal, will cause flickering, but if our cache was too small for the amount of changes that have occurred, we've got no other choice. If we had more memory, we could make the caches bigger, but if we don't, then there's really no other options. So that's what we're doing there. Now, once we've drawn the screen, we will need to actually clear all the caches, and that is what the reset caches function does. All we need to do to reset the caches is basically load in the cache addresses from the backup and write them back into the current ones. Remember, we were updating that current position at various points here. That's what was happening here. But what we need to do to reset things is load in the original positions from the backup to the current, and that's what we're doing here, repeating for all of the cache count there. Now, once we've actually done the initial caching of the data, there will come a point where we want to draw that to the screen. And that's what process cache does. We need to execute this with IX pointing to one of the caches. So we either process these through in sequence, all three of them, or we wait for our raster line and do them at more appropriate timing to try and minimize the flicker to hopefully 0. Depends how much is changing on the screen though. So that's what's going to happen here. So basically what this is it's similar to the drawing routine in the double buffered version we saw last time that drew directly to the screen, but this time we're reading our data in from the caches. So what we're doing first here is we're loading in a byte. This is the count of the tiles, and if this is 0, we're running process cache 0 because that's a special case. Otherwise we're loading that into IYL as our count. Then we're loading our VRAM destination from HL into HL here. We're then loading the tile map source address, the pattern data, into BC in the shadow registers here. And then we're assuming we might want to use stack misuse. So we are basically caching the current stack pointer address here because a lot of these routines use stack misuse for speed. There's an alternative version of the drawing routine for the CPC if we're shifted 4 pixels down. The VRAM destinations are a bit complicated on the CPC, but I wanted 4 pixel shifts, and it was best to have a second version of the code rather than a slower one that was flexible enough to do both. This is some test code, just slows things down. We won't look at that. Here we're loading in the tile, and once again we are seeing if this tile needs to be drawn and drawing it if it does. Now we worked out the first draw position and the last draw position, skipping any unneeded tiles, but within the middle there may still need to be the odd tile that is skipped. It didn't seem appropriate to do all of that with caches. We could have cached every single tile that needed to be drawn in odd positions, but the amount of extra bytes of new VRAM destinations seemed prohibitive. It didn't seem to really be very memory efficient and didn't seem likely that would actually give any benefit. So we're only skipping entire lines and skipping the start and the end that don't need to be drawn. So we are still needing to check if these tiles have flags that need to be drawn here. Once we've drawn a tile, once again, we are updating our VRAM destination, moving across the screen 8 pixels as is required by each system. We're then repeating for the current line, and then we are restoring our stack pointer here, enabling interrupts if required by the system. We're then moving 5 bytes to the next entry within the cache for the next line to be drawn to the screen. Each line is 5 bytes. That's 1 byte for the count, 2 bytes for the VRAM destination, and 2 bytes for the tile map source. We're then repeating, doing the next line until we are complete. Now completion is actually defined by the 0 byte here. That is the process cache 0. Those are the special commands, and that is done by this code down here. Now basically we're loading in the DE pair into the shadow registers here from the following 2 bytes from that 0. Now these will be the pattern address unless they're both 0, and so in the case that they're both 0, we're basically done, and we're checking that just here and going to done here, in which case we are finished, and we're writing a new end pointer to mark that this cache has been processed and then returning. But otherwise what we've got here is the new pattern address that we want to use for the remaining draws. So we're loading those into DE. If we are using a tint, we're loading that as well, and then we are basically moving along within the cache and continue processing, because as I say, if it's not a 000, this is just a pattern address that we're using for drawing the data. And that's how this works. It's a little bit complicated, but it works pretty well, and it does significantly reduce the flicker. As I always say, go to my website, download the source code build scripts, have a go at it yourself, and if you can use anything in it, go ahead and do so, even if it's just taking ideas. I'm certainly not suggesting my code is the best. It's just what I was able to do, and I hope you can get some benefit from it. As I've said before, if what you saw today is too complicated, please stick around for the platform-specific lessons, because the draw tile routines there you can take those out and use those independently of the rest of the code. They're self-contained. They just draw a tile to the screen, and they do it fairly efficiently, and they allow X flip and Y flip and transparency. So maybe they're useful to you even if the rest of the code is too complicated. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.